In the last lesson, we met the parts. Now let's watch them work as the standard RAG workflow. The first thing to understand is that RAG isn't one pipeline, it's two. An offline indexing pipeline prepares your knowledge ahead of time. You run it once, whenever your documents change. And an online query pipeline runs every single time a user asks a question. Both pipelines meet at one shared place, the vector store. Indexing fills it, querying reads from it. Across the two, there are 7 steps, and we'll walk through every one. Step 1. Chunking. A whole document is far too long to embed at once, so we split it into smaller pieces. The simplest approach is fixed-size chunks, say 500 tokens each. But cutting blindly can slice a sentence, or a whole idea, right down the middle. So we add overlap. Each chunk shares a little text with the next one, maybe 50 tokens, so meaning isn't lost at the seams. Smarter strategies split on natural boundaries instead, paragraphs, sections, or even shifts in meaning. That's recursive and semantic chunking. And the size is a real trade-off. Chunk too large and retrieval gets vague. Too small and each piece loses its context. Step 2. Embedding generation. Every chunk is fed through an embedding model, and out comes a dense vector, a fixed-length list of numbers, often several hundred to a couple of thousand of them. Each number captures some subtle feature of the chunk's meaning. Together they pin it to one precise spot in a high-dimensional space. We run this in batches, embedding thousands of chunks efficiently, and we keep every vector paired with its original text and metadata. And one rule matters above all else. Remember exactly which model you used, because every query will have to use the very same one. Step 3. Vector storage. All those vectors go into a vector database, but it doesn't just pile them in a list. It builds an index, a structure designed to make search fast. A popular one is HNSW, a layered graph where each vector is linked to its nearest neighbors. To search, the database hops through that graph toward the query instead of comparing against every single vector. It's approximate, but it's lightning fast even over millions of points. And alongside each vector, it stores metadata, the source, date, or author, so results can be filtered later. That completes the offline indexing phase. Now the online phase begins. A user asks a question. Step 4. Query vectorization. That question is embedded into a vector, using the very same model that embedded the documents. This is non-negotiable. If the models differ, the query lands in the wrong region of the space, and retrieval quietly fails. Same model, same space. Step 5. Similarity retrieval. The database compares the query vector against the stored ones, usually with cosine similarity, essentially the angle between two vectors. It returns the top matches, the k nearest chunks, your candidate answers found in milliseconds. Step 6. Re-ranking. That first retrieval was fast, but a little coarse, because it used a bi-encoder, which embeds the query and each chunk separately and never compares them directly. So we deliberately cast a wide net, pulling in maybe the top 50 candidates rather than just 5. Then a cross-encoder rereads each candidate together with the query in a single pass and scores true relevance far more precisely. It's much slower, so we only run it on those 50 finalists, then keep the very best handful, say the top 5. Wide net first, then sharp focus. Step 7. Final response generation. Now we assemble the prompt. The system instructions, the user's original question, and the re-ranked chunks are stitched together into a single context. The language model reads all of it and writes an answer grounded firmly in those chunks, often citing exactly which ones it drew from. And that is the entire workflow. Chunk, embed, and store your knowledge once. Then for every question, vectorize, retrieve, re-rank, and generate. 7 steps, 2 phases, 1 goal. Putting the right knowledge into the model's hands at the right moment.